So today we're going to start discussing something I'm going to call curve sketching. And the question is, how can we use what we know about the derivative to help us draw graphs of functions? So I'm going to start with an example. I'm going to look at this function here. So suppose y equals x squared minus 4x plus 7. Now this one's simple enough where you could probably figure out how to graph this by hand without the use of derivatives, but I'm going to use derivatives anyway. Okay, so we know about parabolas. We know they have U-shapes generally. They either look like this or like this. And the one we're looking at here, since that x squared term is positive, must look like this one somehow. We just know that it's shifted left or right or up or down. Okay. So we'll talk about how it's shifted in a moment. All right. We can identify some nice points right away. For example, you can plug in x equals 0 because that's easy to do. And if you do that, then this first term would become 0, and the second term would become 0, and then y is just 7. So now you know the y-intercept. So you've got 1 point in first street. Okay? As far as the other points, though, it might not be as obvious. So this is what I'm proposing. We're going to take the derivative of this thing, y prime. If we do that, we get 2x minus 4. Now, let's think about what the derivative tells us. It tells us the slope for any x value. So my claim is, if we look carefully at this expression, we can figure out things like when is the slope equal to 0, when is the slope positive, and when is the slope negative. So let's start by finding when this thing equals 0. So if we set y prime equal to 0, we get 2x minus 4 equals 0, so x is 2. So we know now is this, whatever the original graph looks like, that when x equals 2, it's got a tangent line that's horizontal. All right? So now, what else can we do? Well, here's what I'm proposing. We're going to make a little number line, and we're going to mark off x equals 2 on that number line. Here's x equals 2. And we're going to find out what we know about the slope prior to x equals 2 and after x equals 2. So for example, if I pick any number you want over here to the left of 2, let's say we pick x equals 1. And if we sub that in here, y prime 1 would be 2 times 1 minus 4, which is negative 2. And I'm not really worried about what it equals, but what I can say, though, is that since it's equal to negative 2, right, that means that the slope is negative to the left over here. So I'm going to put a negative sign here. All right. So what does that mean? Well, if I'm thinking of a graph whose slope is negative, then really what has to happen is, here's what we know, here's 2. The graph has to be decreasing prior to that. It has to be heading in this general direction. So now I can at least say y is decreasing on that interval. Now, it's important to note, you didn't have to pick x equals 1. You could have picked something else. Maybe you could have gone down here and picked x equals negative 5. Sub that in here. 2 times negative 5 is negative 10, minus 4 is still a negative number. It's negative 14, but it's still negative. So my promise to you is no matter what x value you pick on this side of 2, you will get back negative values for y prime, and therefore the slope is negative, and we know the function is decreasing on that interval. All right? All right, next thing. Over here, pick a number out here, let's say 5, for example. So if x is 5, and we do y prime of 5, we get 2 times 5 minus 4, but that's equal to a positive number. Notice that I don't even really care what the answer is. I just care about the fact that it's positive. Okay? So what do I know? Functions that are positive generally move in, or have positive slope, I should say, move in a direction like that. So on this interval, I can say y is increasing. You might object a little bit to this idea of just plugging in numbers and then trusting that every place else is also going to be negative. Right? Take a look at this expression for a minute. We know that 2x minus 4 is a line when it's graphed. Right? So it doesn't do any turns. In other words, it's heading in a general direction, and that's it. So it's equal to 0 at one time when x equals 2. And after that, it never equals 0 anyplace else. Right? So let's think about it. We're prior to x equals 2. There's no way that there's any number over here that I can plug in that would give me a positive value. Because if there were, then that means that this graph had to have crossed the axis again, and we would have had a second place where x equals 0. So you actually can trust this technique. It's sort of fun. Go over here on this side, and you get the same reasoning, right? At x equals 5, we got back a positive number. Someone might say to me, hey, well, how do you know that when you go out to say maybe x equals some large number like 100 or something else, that maybe when you subbed it in, that you might get a negative number somewhere? Well, if I had, then that means that this graph crossed the x-axis again, was equal to 0 at some other point. And that didn't happen. Or it can't happen because this is a line. And since it's a line, it'll cross the x-axis in one spot. So that's how we're being able to use this trick. So now we actually know the general shape of the function. What we know is, here's our x and y axis. We know that x equals 2. There's a horizontal tangent somewhere. Now, since that's a point of interest, I'm going to rewrite my original function again. Here is x squared minus 4x plus 7. Let's just remind myself I got that correct. I do. I'm going to plug 2 in there. So y of 2 is going to be 2 squared minus 4 times 2 plus 7. Or 4 minus 8, negative 4, plus 7 is positive 3. So I know that this thing goes to the point 2 comma 3. And I also know that at that point, the tangent line is horizontal. So I'm drawing a little horizontal tangent line. I know the graph has to do one of a few things, right? So here's something it might do. It might go like that, right? And at x equals 2, have a horizontal tangent. It might go like this. At x equals 2, have a horizontal tangent. And there's still a few more options. What else could it do? It might do this. Here's x equals 2. It might come up, level off, and then continue up. Right? And then lastly, it might do this. Here's x equals 2. It might come down, level off, and then continue downwards. All right? So the next part of our job is to decide which of these cases have occurred. So this little green line here is just representing the horizontal tangent. Is how can we use what we stated in this number line up here, this testing that we did, to help us decide between these things? Let's use this thing circled in black here. What do we know? We know that when x is prior to 2, that the slopes of the graph are negative. That means the graph has to be decreasing. So it must be heading downward somehow. And then when it gets to this point, it levels off because we know it's getting a slope of 0 at 2. And after that, we showed that all the slopes beyond 2 were positive. The graph must do something like this. Okay? So this is the beginning of curve sketching. Now, I'm leaving something out about concavity, which we'll learn a little bit more about in maybe a different lesson. But for now, this is something you should be able to do. All right? Let's try another problem. So here we go. Let's look at f of x equals x cubed minus 9x squared plus 15x plus 2. And you can start by maybe finding the y-intercept. That's easy to find. Let x equal to 0 and see what you get. You're going to get 2 here. But then take the derivative and make a number line and see what it tells you. Okay, so the y-intercept's easy to say. F of 0 would be 2. So you know you at least have one point on the graph has to go through. But let's look at the derivative again and see what it can tell us. So f prime of x is going to be 3x squared minus 18x plus 15. Okay? So the most natural thing is to start out by trying to find out, hey, when does this thing equal 0? So we'll do that. We'll set this thing equal to 0. And let's try factoring. So there's a common factor of 3 I can take out. So 3, I'll have x squared minus 6x plus 5 equals 0. And then that's factorable. If it wasn't factorable, you'd have to resort to quadratic formula. But that looks pretty good. So now you know at x equals 5 and at x equals 1 that the slopes of the tangent lines are 0. Okay? So just like back in this problem, we found one point where the slope was equal to 0, and then we had 4 different cases to consider. Now we have 2 points where x is equal to 0. I'm sorry, the slope's equal to 0. And therefore, for each of those, we're going to have to consider what might be happening. So we'll use the same trick. We'll start by making a number line. And we're going to call this number line f prime of x, because it tells us about slope. And we're going to mark off these numbers, 1 and 5. And what we're interested in finding out is, hey, what happens between these numbers? So what happens on this first region? What happens on this second region? And what happens on this third region? What kind of slopes do we have? positive or negative. All right, so let's start with the first one. We'll pick a number in here. Okay. Maybe we pick x equals 0. Now you have the option. You can plug it into the derivative in any form. You can plug it in this form, or this form. If you ask me, I would pick this one. Here's why. Because I don't actually care what the answer is. I just care if it's positive or negative. So for example, if I put 0 in here, 0 minus 5 is a negative number. If I put 0 in here, 0 minus 1 is a negative number. Okay, a negative times a negative is a positive, times the 3 that's out here would still be positive. So I know in this first part of the number line that the slope will be positive. And that tells me that f of x, the original function, must be increasing. So x equals 2 maybe. So 2 in here would be a negative number. 2 in here would be a positive number. Negative times positive, negative times 3 is still negative. So now you know that f of x is decreasing here. All right? And then lastly, we'll pick here maybe. Say we think x equals 6. We could sub that in here. So 6 minus 5 is positive. 6 minus 1 is positive. 10 is positive, times 3 is positive. And there you go. And now you know that f of x is increasing again. Okay. So now we have some sense of what the graph must look like. It's got to be going up, going down, and then going up again. So it's going to have that general shape. Okay? Well, let's be a little bit more specific, because we actually know the two places where the slope is equal to 0. So my suggestion is let's at least get the y value there. Exactly what the original function was. There it is up there. F of x equals x cubed minus 9x squared was plus 15x plus 2. Plus 15x plus 2. And we know that the f prime of 1 was equal to 0. We also know that f prime of 5 was equal to 0. Those are two places where we had horizontal tangent lines. What I'd like to know is the y values there. So I'm going to do f of 1. So f of 1 is going to be 1 cubed minus 9 times 1 squared plus 15 times 1 plus 2. I also want to know what f of 5 is. F of 5 is going to be 5 cubed minus 9 times 5 squared plus 15 times 5 plus 2. So you have 9 and negative 23. Okay, so what we can do now is at least graph those points. We actually have a few points. We know it goes through 0, 2, through 1, comma 9. So up here maybe we'll make this the point 1, comma 9. And then we also know it goes through 5, comma negative 23. Now that's not really to scale. This should actually be going down much further, but I'm going to run out of space. All right, so we know the graph has to do things like that. And we also know that at these 2 points, the slopes of the tangent lines are horizontal. Okay? What else did we learn? We learned that f of x was increasing on the interval negative infinity to 1. And it was also increasing on the interval 5 to infinity. We also learned that f of x was decreasing on the interval 1 to 5. And we did that with our number line here by testing and so forth, and we figured out here it is increasing, and there's the decreasing interval. All right, so we got to make a graph that does this. Well, here we go. I'll try it out. So it's got to go through this point, so it's increasing. When it gets to this point, it has to level off. It has to sort of become horizontal. Okay? Then it's got to decrease in between and come down and level off again because the tangent line becomes horizontal again. And then lastly, increase thereafter. So this might be what the graph looks like. All right. First off, yeah, we've got a couple issues. First off, if I wanted to, I could find this point by setting y equal to 0, like make this thing equal to 0 here and try and solve that. And if I did that, I'd be able to figure out what this x values are across the x-axis. But there's another x value in here that's actually pretty important that I'd like to emphasize, and we didn't discuss, but we will in a future lesson. And that is, if you think about this graph, this part of the graph here that I'm highlighting in green, compared to this part that I'm going to highlight in red, there's something different about them. So actually, for the green part of the graph, what we notice is x gets bigger, the slopes are actually getting smaller. And you can see that because if you look at this tangent line, that's really pretty steep. That one's flatter, that's 0, this is negative. So for the first part of the graph, the green part of the graph, it's concave down. And if we look over here over the red part of the graph, we know that as x gets bigger, the slope is getting bigger. Now, it might be misleading at first. Like, this slope seems pretty steep, and that seems less steep. But remember, that slope's probably something like negative 10, while this slope's only something like negative 1. And if remember, negative 1's a bigger number than negative 10, right? And over here, all these slopes are getting more and more positive. It's steeper and steeper in the positive direction. So this part of the graph is concave up. So what we didn't discuss today is how to find out this magic point, this point here, which is referred to as an inflection point. An inflection point is a point where we switch concavity. We switch from concave down to concave up, or vice versa. So we'll need to think about that in the next lesson.